Oh, okay. We can go over that again if you want this evening, just specifically what you got stuck with. All right, so but let's cover what we were meant to cover this evening, and that's the normal distribution. All right, so I am recording and just double checking. Yeah. All right, so in tonight's session, this is it's quite an important section in this module. And the reason I say that is because this what do you call it? This content gets carried over into the next learning unit. So you will still use it even in the next 2 more learning units. So you're going to use it in learning unit 7 and learning unit 8. So it's very important that you understand it because you can think of it as kind of like a foundation for the learning units that are going to follow. Right. So it's very important that if you don't understand something, you've got to tell me. Right. I need feedback from you to tell me that you're not understanding something, or you want me to go back and explain something. So please, I need your feedback on this. All right. So let's start by sharing my screen and to kind of give you an idea what the normal distribution is all about. Okay. Now the normal distribution is easily one of the most important, or if not the most important, distribution in statistics, not just from a course perspective, but in the real world. There's a lot of, I would say, estimation and inference that's made about things based on a normal distribution. So it is a very important distribution, right? And what do I mean by distribution? Well, if you recall earlier, much earlier in this course, I spoke about, oops, let me second, spoke about something called a distribution when you looked at a histogram, right? So let's look at a histogram of something, and if let's say we're plotting a histogram of students' marks. So we just looked at one class, right? Let's say this class has about 80 students, and we look at what their marks are and we plot a histogram for them. Okay, so the first bar here would be, let's say, students that scored between 30 and 40. Then the next mark would be 50. Next mark would be 60, 70, 80, 90, and 100. Right, so we plot this histogram. So this, you here on this axis. Yeah, so I know I did it badly. Let me just try and do it neater. Let's do a line here. What you have on the y-axis is your count. Okay, so your y is actually your count or your frequency, right? So what we're saying here, the amount of students that scored between 30 and 40 marks was, let's say, 10 people. Okay, then here, there's a bit more students, let's say 15 of them, that scored between 40 and 50, and 20 scored between 50 and 60, and so on and so on. Okay, so the numbers are increasing like this. We get more and more students scoring higher marks until we get to the 70 mark. But then after that, the numbers are dipping again, because there's not many students that are scoring very high marks. So you get this shape here, like that. All right. Now you could see I've only got 1, 2, 3, 4, 5, 6, 7 bins, right? If we had to go more granular, like let's say instead of 30 to 40, I go 30 to 35, right? And then 40 to 45. I could make this histogram a lot more finer, like that. Okay, you get more granular, more detailed information, and so on and so on. But what we're really interested in is in the shape of this histogram. So in other words, if I draw a green line, just joining the corners of these blocks like that. If I get something like a bell shape, so let me just erase everything now. Just keep this green line in mind. So I'm going to erase everything and then redraw this, just the green line. Okay, so if I draw this, the green line, it goes like this. Like that. So it looks like a bell, right? And what I mean by like looking like a bell, well, let's say this is the highest point here. And if you draw a line straight down the center here, sorry, to draw a line straight down the center, then what you see on the right of that line is exactly what you see on the left. It's symmetrical, right? It's a mirror image of each other. Now this, when you have this occurring, this is a normal distribution. This is a normal distribution. And why this is important is because we can start making predictions and estimates based on this distribution. So in other words, let's say I want to know what is the chance, okay, what's the probability of a student getting more than 70%? What's the chance of someone getting more than 70% for this test? I can work this out using this table in the back of your book, all right? Because if I know that this follows the normal distribution, then I can use this table in the back of your book, right? And I'll tell you what page it is in a second. I'll get there. But just keep this in mind. This is why it's important and how we're going to apply it. If I wanted to work out, say, the probability of a student failing, what's the chance of a student getting less than 50% for this exam, right? I can work this out using this table. So a normal distribution is very handy because as long as you know something follows the normal distribution, you can use this table, right, at the back of your book just to get these probabilities, right? And this is, the example I just gave you now is just about students' marks. It could be about anything. You could be working out water consumption about something, or you could be working out temperature, the probability of a temperature of a device going over a certain value, over a certain degree Celsius, all right? So it's very handy in the real world, and you know it has a very neat property that we can get the probabilities using this table. All right. So let me show you how to get these probabilities, and then I'm going to show you how to apply it. Okay, so I'm going to show you how to get the probabilities first, and then I'm going to show you how to apply it in a typical real world problem. Right. So ignore the text that I have typed out in the top there. Right. And just focus on what I'm writing here with my pen. Okay, so I'm just going to clear this out. All right, so have your textbook with you. Hopefully you got the announcement and you have your textbook with you. All right, so get your textbook. I have the 5th edition. And with the 5th edition, you want to turn to page 506. All right, and that's Appendix 1. So if you have another edition, just whatever page Appendix 1 is, that's where you go to. Okay, so get to page 506. Okay, and you should see this table that you have on the right here, what I've pasted on the whiteboard. Okay, you should see this table that I have here. All right, let me just check the chat if anyone's lost or anyone has any questions. And what page? I think I just said it was 506 on the 5th edition textbook, page 506. 506. All right. Okay. Okay, you good? Got it? Fantastic. All right. Let's get there. Now, you see this table has a Z value on the top left corner here. Right? If you look at it, it's got this Z value here. All right. And there's a graph here. Okay, there's a graph that you have on the top. It's very important that you understand what this graph is all about. Okay, so you got this graph here. Okay, and it's drawn like this. The bell shape, just like what I showed you earlier. That. Okay, and then you have this blue region shaded in here. At 0. I'm going to try and do it exactly what you see in your book. Okay. There we go. And you got this blue region shaded in here. Okay. I won't shade it in completely, but you get the idea. All right. So now, what this graph tells you, okay, and this table. So the values inside the table are probabilities. In other words, it's the area under the curve. So in other words, if you want the area between 0, okay, so I'm going to write it like this. If you want the area between 0 and let's say 0.2, right? You want the area between 0 and 0.2. So here's 0. If you look at your graph, there's 0 there, right? And this Z is what value you're looking for. So in our case, it's 0.2. So what it's telling you is that here's 0.2 on your Z value. If you look at Z, there's Z. So if you go down, Z is 0, 0.1, 0.2. There's Z being 0.2. If you go along the right, the values on the border, on the margin here, tells you the second decimal. So in other words, here's 0.2. If I look at the first column here, then that's just 0.20. If I look at the next column, then it's 0.21. Then here it's 0.22. You get the idea. So that's just your second decimal. But for us, we don't care about the second decimal because we are looking for 0.2, exactly 0.2. So that means it's the first column because there is no second decimal value. All right. So here the 0.2s, it's this row and it's this column. All right, 0.2. And the value that is there, that intersects between that column and that row, at 0.0793, that is the area here. When you're Z, that is this area here. This is 0.0793 when Z is 0.2, right? So in other words, if I had to draw this again, here's your curve. All right. Here's your 0 mark. Here is 0.2 on your Z-axis. Then this area between 0 and 0.2, this area here is this value here, 0.0793. That this area here is 0.0793. Okay, do all of you understand that? Is that clear? No? Just let me know if you don't, if that doesn't make sense. Right, so let's do another example. Let's do another one. Right, so now instead of 0.2, let's say I want the area between 0 and 0. And then not instead of 0 point, let's do 1.11. Okay, so now the value here is 1.11. So now I want the area between 0 and 1.1. Okay, so here, there's your 1.1, but you can see there's a second decimal. All right, so then it's not the first column, it's the second column, because there's your 0.1 here. So it's this column here. So where those two intersect, 1.1 and this column, it'll be here So this area now is what I've just circled, 0.3665. 0.3665. Okay, let me check the chat if anything. All right, so now maybe as a quick exercise, you can look at the table that I have here, or you can look at it in your textbook. Give me the area now instead of 1.1. I want you to write this in the chat. What is the area between 0 and 2.55? 0.55. What is the area between 0 and 0.55? Use this table and write it in the chat. Okay, give that a shot. Good, Thomas. Very good. Yes. Okay, so hopefully everyone understands that the area between 0 and 0.55 is just 0.55, and the second decimal is 5, so it will be here. Where they intersect will be here, 0.2088. So this area here is 0.2088. All right. Okay. Now let's do something a bit different. So I'm going to erase this. Okay. So far, what I've been asking you is, the one I just asked you now is, I've asked you to find the probability of Z being between 0 and 0.55, right? And that was 0.2088. Okay, if I'm reading from the table. All right, now this table, right, that you see here, everything that you see here that's in your textbook, it'll only give you the area, right? So if I had to draw this, it'll only give you the area from 0 to whatever value you're specifying. In our case, this is the value we're specifying, so 0.55, right? So that means it'll give you the area from 0 to that Z value that's on the right of it. Okay, so here, this is the area it's giving you. But what you're working out is the probability of Z being between that. What if I want to know what is the probability of Z being greater than 0.55? So now, what I'm asking, the question I'm actually asking now is, instead of the blue area, I want to know the area on the right of 0.55, because I want to know what is the chance of Z being greater than 0.55. So that's everything on the right of it. So I need to work out what is this green area here. All right. Now, what we're going to do to solve this is this entire area under the graph can only be 100%, because remember, the probability of everything cannot exceed 100%. So the area under the curve, the entire area under the curve is 1 or 100%, right? The entire area of the curve is 100%, 1. But the normal distribution has a unique property. Now, if you recall, when I started off this session, I told you that the normal distribution is a bell-shaped curve and it's symmetric. That means what you see on the right is exactly what you see on the left, all right? You have an identical image here as you do here on the right and left of this black line. So if they're identical, or you can think of them as being equal to each other, if the entire area is 100%, and if this black line at 0 is splitting it into half and half, then that means half the area here, this entire area in black, is 50%. okay, 50%. And the entire area on the right, everything in the right here, the right, is also 50%. Or in other words, 0.5, same thing. But now remember, you've already worked out this blue area. This blue area here that I'm going to just circle, you've just worked it out. It is this here. That's 0.2088. So this green area must be the remaining area of the 50%. So in other words, this green area, right? This green area is simply just 50% minus this value here, 0.2088. Or in other words, 20.88%. And if you work that out, then that's the area in green. Okay. So I'm just going to get my calculator. I actually don't have it here. A second. But if you want, you're welcome to work it out. Write it in the chat. You should get a value of 0.5 minus 0.2088, and that gives you a value of 29.12%. So that green area is 29.12%. So that's what this area here is. The answer to this question here is 29.12%. Okay, is that clear? Is that making sense? Thanks, Heyman. Okay. Okay, no problem. Let's go back to the board. All right, so let me clear this audio. Okay, let me try and explain this one also in another way, right? Let's say I went back to that histogram example I gave you, okay? Yeah. Okay, so remember earlier I did the histogram, and let's do it this way. Okay, so let's say the marks went from 40 to 50, 60, 70, 80, 90, 100. All right, so now instead of on the y-axis, instead of giving you the frequency count, right, I'm going to convert it to percentages. So that means here only 5%, right, 5% of the class scored between 40 and 50. Here, 20% scored between 50 and 60. And then here, let's say 50% of them scored between 60 and 70. This is the same as here. And here, let's say this 2%. 2%. But the question is here, if I had to ask you, right, what percent of students scored between, and I'm going to write it as a probability, sorry, mathematically, scored between 40, so scored between 40 and 60. What percent of students scored between 40 and 60? All right. You can see between 40 and 60 are these two blocks here. I'm going to shade these blocks in blue. Okay. There's 40 and it goes up to 60. So altogether, there was 5% of them and 20%. So in other words, that is 25%. So the answer is 25%. 25% of them. But what you're actually doing is you're actually answering the question, what's the chance, what's the probability of someone scoring between 40 and 60? And the way you answered it is by finding the area under this curve, roughly. That's what you're kind of saying. So that's what we're doing here when I'm asking you what is the probability of Z being greater than 0.55, right? You're working out an area for this given range. So let me clear this and go back to what I did earlier. Okay, so okay, so let's go back now to the question I asked earlier. It was, what's the probability of Z being greater than 0.55, right? Now, we are going to use this table to get it because here's the distribution. It's drawn for us, and we have to use what's given to us in the table. So let's draw what you're trying to solve, okay? So we're asking to work out the probability of Z being greater than 0.55. It's important that you're able to understand visually what you're trying to do here. Okay, so I'm going to draw this curve. So all I'm doing is I'm replicating what I'm seeing here in my graph and in the table and in the textbook. I'm replicating this, right? So there's 0, right? And there's 0.5. For our specific question, we're looking at 0.5, so that's a positive value, okay? Positive 0.55, so it has to be on the right of 0. So it's here, 0.55. So we're asking, what is the probability that Z is greater than 0.55? So greater than 0.55 means everything on the right of it, this blue area here, because we're saying greater than 0.55. Remember what I said earlier? Probability means we're finding the area under the curve. And for this example, we want to know the area on the right of 0.55. That is when Z is greater than 0.55. So you need to find this area here that I'm shading in blue. And if you find this area, then you've answered the question. Okay, however, if you look at the textbook, and it's very important you understand that the graph that's being shown in the textbook doesn't give you the area on the right of Z. If you look at Z here, what I'm circling, it doesn't give you the area on the right, it gives you the area on the left of Z. Okay, so your textbook instead is telling you that you can find the area on the left of 0.55 and between 0, and that you can find in the table. Okay, because that's what we've been doing all this time. Okay, when we started this section, and I gave you that question to do and answer in the chat, you were finding the area between 0 and that Z value. Okay, so you can find the area between 0 and 0.55 by just looking in your table, which is what you did. There's 0.55 here, intersecting here in this column, and the value you got is 0.2088. So this purple area here is 0.2088. But I'm not interested in the purple area. I need to solve the blue area. What is the value of the blue area? This is what I need to figure out. And how I do that is I use a property of symmetry. Okay, now the area under the entire graph, that is the probability of everything, right, is 100%. Do you remember a probability cannot exceed 1? So in other words, the area under the curve is 100%. And the normal distribution splits that area equally in half at the point 0 here. Okay, so at point 0, if you draw a vertical line down here, the area that you see on the left of that line is equal to the area on the right. That means this area on the left is 50%, and the entire area on the right is also 50%. Okay, this entire area on the right is also 50%. So if the entire area on the right is 50%, and the purple area is only 20.88% or 0.2088, then this question mark, this area here has to be the remainder. That question mark has to be 50%, or in other words, 0.5 minus 0.2088. And that's how you get the value of 0.2912, or in other words, 29.12%. That's the answer to this question, the blue area. Is that clear, everyone? All right. Okay, it's very important you understand that. Okay. Okay. Okay, we're gonna do one more. Let's do one more. And then I'll show you how to apply this to a real problem. Okay, let's say you've been asked, now, what is the probability that Z lies between a value of minus 0.8, okay? So Z is between minus 0.8 and 1.1. Okay, now you can see before we used to have 0 here, but now it's at 0. Now it's minus 0.8, okay? So let's sketch what we're trying to solve. It's very important we sketch it so we understand visually what we're trying to work out. Okay, so if I sketch this curve, this bell-shaped curve again, okay, there's our 0 at the center point here. And now the Z value here is minus 0.8. Now, because it's a minus, it has to be on the left of 0. Okay, so negative numbers will be on the left of 0. So there's minus 0.8. Right? And on the right, it's 1.1. So that's a positive number, so that's on this side. 1.1. 1.1. So what we're asked to work out is, what is the probability that Z is between minus 0.8 and 1.1? In other words, what is the area between these two values? What is this area? So I'm going to shade this. We are trying to work at this entire area, right, between these 2 points. But I'm going to shade it in 2 different colors, because to work it out would involve having to treat these areas separately. So this area between 0 and minus 0.8, I'm going to shade it here in pink. Okay, and then the area between 0 and 1.1, I'll shade it in green. Okay, so to answer this question, we simply just need to work out what the pink area is, what the green area is, and add it up. Okay, that's the answer. So the answer to this question, let's call this area in green B. We'll call this area B, and the area in pink is A. Okay, and if you just know A and you know B, add them up and that's your answer. Okay, does that make sense to you conceptually? Everyone, before we go on the how we're going to do it, in the left. Sorry, I'm not sure which question you didn't mean to get on the left hand side. Is it the question I'm talking about right now? So on the left hand side, the minus 0.8. Yeah, yes, exactly. Because it's a minus number, it's on the left of 0. it's a positive number, it'll be on the right of 0. Okay, so we're splitting this up into two components, right? If we work out A and then we work out B, all we're going to do is add them up. So let's do the easier one first, and that's B. The easier one is actually working out B, because that's what we've been doing all along. Because your textbook tells you the area between 0 and any Z value on the right of it. So this you can easily find. Okay, do you want to give that a shot? So this area in green you should be able to find. Okay, you're looking for where Z is 1.1 in your table here, and then find the value that corresponds to it in the table. So give that a shot right now. I'm going to give you less than a minute. So if you can quickly just do that, make an attempt. If you get it wrong, it doesn't matter, because this is where you need to get it wrong, okay, and figure out that you're not understanding something. So I want you to find area B, which is the green area, and that's straightforward. It's in your table. Can you write that in the chat? Good, Vanessa. Yes. Does everyone understand why the green area is 0.3643? So there it is here. There's 1.1 for Z. And remember, there's no second decimal. There's no second decimal. So it's the first column, right? So there is your value here. So the area in green is 0.3643. So what you've worked out is you've only worked out the area between 0 and 1.1. Means, okay, that's what you worked out. You worked out the blue area. In fact, B. You worked out B, which is the green area. Okay, 1.1. Okay, so we've got B, and that's this here. This is B. Okay, now we're going to try and work out A. All right. Now A, it may just seem tricky to you because it's on the left. Okay, but let me redraw this, and you'll see actually how easy it is. Okay, I'm going to erase all of this here. Okay, I'll re-sketch this. Okay. Cool. Let me just change the color here. Black. Okay. Now there's 0, and that's the middle point, right? Point of symmetry. Yeah. Now remember what I told you about symmetry, that everything on the right of 0 is identical to what's on the left of 0. That's the whole idea of symmetry. It's symmetrical. You draw a line, vertical line at 0, and it kind of splits it exactly in half. Whatever you see on the right is what you'll see on the left. So in other words, if it really is symmetric, right, where you have a negative 1 point, let's go. Where you have a negative 0.8, you would have its equivalent positive value here, positive 0.8. All right. And because it's symmetric, this is the same distance from 0 as this is from 0. Doesn't matter whether it's negative or positive. Negative just means it's moving to the left. Positive just means you're moving to the right. So in other words, if this is the same distance, right, then that means this area has to be the same as what it is here. So in other words, that pink area that you see there that I've shaded earlier, this pink area here is exactly the same between 0 and positive 0.8. Does everyone understand that? Because of symmetry. I just think about, like, if your face is perfectly symmetrical, if you draw a line down the center of your nose, your left side would be exactly the same as your right side. So the distance from your nose to your left eye would be the same as the distance from your nose to your right eye. So that's why everything is identical, it's just in different directions. So this pink area here, you can easily work it out. All you're going to do is find the area from 0 to positive 0.88. So in other words, the area of 0 less than Z less than 0.8. And this you know how to do. You just did it a second ago for the 1.1 value. It's the same thing, but now you look for positive 0.8. And there it is here, positive 0.8. There's no second decimal. And so the value here is 0.2881. So that's the pink area, 0.2881. So now you have the green area, you have the pink area, and so the final answer is adding them up, adding A and B, and your final answer would be 65.24%. Okay, change the color right then. Your final answer is 65.24%. Or you can write it as a decimal, it's fine. Okay, does it make sense? Everyone? Thanks, Vanessa. Thanks, Thomas. Great. Thanks, Alan. Ethan, nicely done. Cool. Clinton, I'm just going to assume all good, but let me know otherwise. Fantastic. All right. So now we've kind of done all this theoretical work. Now let's see how we can actually apply it in the real world. All right. And that's what this text on the left is. It's a problem that we're going to solve it using the normal distribution. Okay. Let me just make some space here. All right, so this question says, a recent survey by a local municipality established that daily water usage by its households is normally distributed. So I'm going to underline that part there. It's normally distributed with a mean of 220 liters and a standard deviation of 45 liters. Okay, these two values are going to be important. But what's important right now is that they're telling you that this water usage follows a normal distribution. So in other words, I'll write differently here. What they're saying is there's some random variable, x, and we have to use some math notation here, unfortunately. X is basically just water consumption. We'll say x is water consumption. All right, and it follows a normal distribution. All right, so what it means now, remember what I said about a normal distribution? It's a bell-shaped curve. Okay, so it's symmetric. So here, I'm going to draw that bell-shaped curve again. I know we've done it a lot of times already in this one session, but get used to it because it's very important to draw this to conceptualize what you're trying to figure out. Okay, so there's my curve. It doesn't have to be perfect, but as long as you know that it's symmetrical, okay? All right, so here, there's your curve. I'm going to draw a line down the center here. Okay. Now, this question tells you that your water consumption is normally distributed, and it has a mean of 220 liters. So now, why this mean is important is because before, here in this graph, we were always showing you, I was always showing you the center as being 0. It was always centered at 0, okay? All right, but in the real world, in a practical example, whenever something is normally distributed, it isn't centered at 0, it's centered at where the mean is, okay, where the average is. So the mean is 220. So here, this x is centered at 220, wherever the average is. That's your mean, okay? All right. And it has a standard deviation of 45. We're not going to use that right now. We'll get to that. Okay, what you just need to understand right now is that x is a bell-shaped curve. However, it is centered at 220 liters. All right. Now, the first question says, use a standard normal Z table. And I'll explain how to use that in a second to answer the following questions. Question 1, what percentage of households is likely to use more than 300 liters of water per day? Now, remember what we said about X. X is water consumption. And the question is saying, what's the percentage or the chance that a household uses more than 300 liters? So what they're asking you to work out is, what's the percentage, or in other words, what's the probability of X greater than 300? All right? And 300 is bigger than 220. So in other words, it is on the right of 220. Okay? So your X value, if you had to do it in order, 220 will come first on the left, and then 300 would be on the right of it. So if they're asking you what's the probability of X being greater than 300, remember what we said about probabilities and the normal distribution? It's simply just finding the area on that region. So X greater than 300, it means everything on the right of 300. So we're trying to work out this area here. This area on the right of 300. And if you work out this area, you've solved the problem. That is the probability or the percentage of households using more than 300 liters of water. I'm just going to pause it for a second and check everyone's following. Any questions? Okay, all good, but just let me know otherwise, all right? We'll come back to the whiteboard. Okay, so now we've drawn this bell-shaped curve in terms of X, but this doesn't really help us much because the curve we have to work with is a Z curve, which is centered at 0. Okay, that's the only table we got. We don't have a table for water consumption. But there is a neat trick that we can do to X to make it Z. Okay, so we can convert this X to Z. In other words, what I'm saying is I can convert this graph that I've drawn in black, okay, to an equivalent graph like what you see in your textbook, but in terms of Z. So what I'm going to do below it is, instead of X now, okay, maybe I drew it too close to the bottom. Let me draw it a bit higher so there's some space. Yeah. All right, so I'm going to sketch this curve below it. It's the same shape, exactly the same shape as what you see in the black curve. But now it's not going to have X on the axis, it's going to have Z, because that's what we need. We need Z because our table in the back of our book is a Z table. And instead of being centered at 220, we're going to center it at 0 instead. So we're going to convert everything in X to a Z value. And how we do that, how we go from X to Z, is you simply use this formula here in your formula sheet. You don't have to memorize it, it's given to you. The formula is this. If you want to work out the equivalent Z, you use this equation here. Z equals X minus mu all over sigma. So for instance, right, if I want to know what is the equivalent Z value when X is 300, right? What's the equivalent Z value? And I simply use this equation here. And where I see X, I'm going to put 300. Where I see the mu, and you would be familiar with the symbol now. We did this in the earlier learning units. Mu is the mean. Okay, so your mean is 220. And your sigma, this is where that standard deviation is going to come in now. That sigma, as in the question, is 45. There's your sigma, 45. Now, if you substitute that into this equation, all right, you'll get an equivalent Z value of 1.78. 1.78. So now, if you want the area on the right of where x is 300, that's the same thing as finding the area on the right of z being 1.78. That's what you're doing. You're finding the equivalent area on the right of the z is 1.78. In other words, this just becomes probability of z being greater than 1.78. And now we're back to what we were doing earlier. We know how to do this because that's what we've been doing all this time in the session. Now you can use this table here, and find that probability like what we were doing earlier. And if you work that out, okay, that'll be 3.75%. 3.75%. I won't go into detail how we did it because we've been doing this earlier. You can try this as an exercise. But the idea for this problem is to show you how you can convert any random variable, x. It can be anything. It can have a different mean, right? As long as you have its standard deviation and a mean, you can convert it to a z value. And then you can use the table in your book. Everyone following? All good? This is how you apply it in the real world, right? Cool. So on the next question, let me just clear this now. I'll check the chat in a second. Okay, let's move on to question 2. I will check the chat in a second. Okay, question 2, right? What is the probability of finding a household that uses less than 100 liters of water per day? So now it's the same thing as what we did in question 1, but now we're looking at where x is less than 100. So we want to solve probability of x less than 100. So now if I had to draw this curve in terms of x, okay, remember now we have x here, which is centered at 220. And now we're talking about 100. So 100 is less than 220. So in other words, 100 will be on the left of it. It doesn't have to be accurate. You just need to have an idea whether it's going to be left or right. Okay, 100 is on the left of 220, so it's here. All right, and we're saying x less than 100. So that means everything on the left of 100, less than 100. So everything here. If we find this area, then we've solved the problem. Okay, so what we need to do now is we need to find the equivalent z value. So we're going to do this. I'm going to sketch this z curve below it. And you don't have to draw these curves, but I do encourage you to do it because it does help you put things in perspective what you're trying to solve. But if you get good enough and fast enough to do it without it, by all means, you don't need to. Okay, you just need to get the answer right. That's important. So now you got your equivalent z curve, and that's centered at 0. And I want to know what is the equivalent 100 in terms of z. And that's why I'm going to use this formula here. Okay, now instead of 300, I'm going to put 100 in because that's what my x value is. Okay, so you're going to put in 100 for x. Your mu, that's 220. Okay, and your sigma in the denominator, that is 45. Okay, so if you write it in terms of z, so it's going to be 100 minus 220 all over 45, and that gives you a value of minus 2.67, minus 2.67. Okay, so now that's the equivalent area that I'm shading in blue here. So you would use, so now you're trying to work out the probability, okay, of z less than minus 2.67. And you would go use your table to solve it like what we did earlier. And this value, you can do it as an exercise, and I do encourage you to do it. I'm going to write the answer, and I want you to work towards it, okay? But if you get stuck, then let me know, okay? Please do contact me. Your answer for this question, all right, is, I'll write it here, is 0.38%. So your answer would be 0.38%. Okay, it's the same thing here. Sorry, 0.38%. That's your final answer. And, yep. Okay. And, did I take? Okay, you're asking me what question? Yes. For wait, question. Are you asking me for the first question? For question 1. For question 1, it was. I was actually doing for question 1. Okay. It was 50% of 0.5 minus 0.4625. 0.4625. Let me just make some space here. 0.4625. That's how I got 3.75%. 3.75%. And how you got the 0.4625? Remember in question 1, so I'm going to clear this. I need to make space here. Sorry, people. I have to. For question 1, okay, we had probability x greater than 300, and we converted that to a z, so it became probability of z greater than 1.78. Okay, 1.78, right? So if you sketch that curve, okay, yeah. There's 0. 1.78 is on the right of it. 1.78. Okay, and we want to know this area in blue. This is, so let me shade it in a different color. I want it in green. The area I want here is this area. That's the answer. Because we're saying z greater than 1.78. So I need to know this area in green. If I find this green area, that's the answer. Okay, but remember your textbook doesn't give you the area on the right of z. It gives you the area between 0 and that z value. So this, your textbook will give you this blue area instead. Now this blue area that I'm shading here, that is the 0.4625. So you can check it. Oh, I don't. The table doesn't. The screenshot doesn't go that far, but your textbook does go further down, 1.78, and you can check that now if you want. And you should get a value of 4.4625. See if I have it open. There we go. There's 1.7. 1.78 is here, this column. There's your value here, 0.4625. So that's how I got the 0.4625. So then, yeah. Tim, does that answer your question? Quentin, thanks, Quentin. Oh, well, for question 2, Question 2, I got 50% minus. Yeah, that's right. Exactly. Very good. That's exactly how I got it. 50% minus 4961. Very good. Yes. So yeah, I want you to do question 2 as an exercise. You have the final answer. And I do encourage you to do it. So for question 2, try to get to 0.38%. I think Kaylin's already put the working on the chat about how to do it, but please try and do it on your own, because it's very important you understand this, because this is going to be the foundation for the next 2 learning units. So make sure you understand this, okay? I did provide an exercise in your pacer. Let me just there's exercises for all learning units, okay? So I'm hoping all of you are working through that. Let me just get there. And yeah, it'll be under pacer. Now, I've just given you some exercises. You're welcome to work through more, please. If you go to your pacer, you'll see we're on learning unit 6, probability, okay? And sorry, we're on section 8. What are we on now? Learning normal distribution. There we are. Normal distribution. Okay, so read through chapter 5, pages 144 to 160. That's in your textbook. And the activity I'd like you to work through is in your workbook, page 115 of your workbook. But you're welcome to work through more exercises in your workbook. The more, the better, and I do encourage you to do that. All right. So do that to consolidate your work. I'm also going to make some practice tests available. They're not going to count towards your final mark or anything. It's just to, give you an assessment to practice these types of questions. All right. So just the only assessments that are going to count to your final mark is your ICE task. But the practice tests I'm going to make available, they don't count towards anything. Okay. So it's left to you if you want to do it or not. But I do encourage you to do it. All right. Okay, I hope that's clear. Please, any questions? Vanessa, I know you had a question about the probability tree. So yeah, if you want, I can cover that now. Is there anything specific on the probability tree that you didn't understand? If it's the entire thing, and you know what, I'll just set aside another session. I'll just go through it again. I'd rather do that. But if it's just one component, what did you prefer? To just address that one uncertainty, or you want me to just cover it again in another session? You got to tell me.
Oh, sorry, Darren, were you talking to me?
Yeah. You asked about the probability tree, right?
Yes, I did.
Okay. Is it just one aspect of it, or is it pretty much the entire thing, the concept? And it's no problem. If you don't understand the entire thing, I'll just set aside another session and I'll go through it again.
Yes, I don't understand the entire thing, unfortunately.
Okay. That's no problem. I'll make a note of that, and then I think next week I'll just go through that again. All right. Yeah,
Hi,
I'll set
Darren.
aside next week's session. Thomas, hello?
I just out of interest, of all these learning units, which ones in the past have the most students struggled with?
Oh, that's a tough one. I don't really have the stats for it, but I think and I'm taking a guess here, for 2 reasons. One, because in the exam, you don't do all the learning units. Students tend to choose which learning units when you do have a choice, and that's the next learning unit. So sampling distributions. Very often, I don't see students choosing that learning unit for when it comes to the exam. So that's how I'm basing it on.
I hear you.
Yeah, and this, what we did in today's session, carries over into that. So that's why it's very important you understand this, because the next learning unit just pulls on that.
All right, thank you.
No problem. All right, everyone.
Did you see my AS task? I got 100%, the latest one. I think it's learning unit 3 or something. Chapter
Right,
AS task 3.
oh wait, you ice task.
Yes, AS task.
Yeah, nicely done. Well
Doing
done.
very well. Doing very well.
Yeah, keep it up. Keep that up.
Thank you.
I'm glad you did it. I'm glad you actually yeah, you're doing your ice task. If all of you could finish it, that would be great. Don't leave it for the last minute. So yeah, you can finish all 4 of them already. You covered all of the content. So please complete them when you can. All right, so yeah, I'll go to probability trees again in the next session, and that's it from me this evening. Have a good evening, everyone, and we'll chat soon. Go for it. Oh, there's just a thumbs up. My bad. All right, cheers.